Hello and good afternoon friends, welcome to the CEC EduSet live lecture. Dear friends, with our ongoing series on coordination chemistry, today we would be discussing on crystal field theory. We would be seeking answer to how d orbitals are split into octahedral, tetrahedral and square planar fields. And to give answer to this particular question, we have once again with us in our studios Dr. Shilpa Mehta. Dr. Shilpa Mehta is Assistant Professor in Department of Chemistry, Ramjas College, University of Delhi. So let's welcome our guest Dr. Shilpa Mehta and let's try to grab maximum knowledge through her experience. Hello ma'am, welcome.
Thank you so much Keetika. A very good afternoon to all my viewers. Now, in the last lecture on the series of coordination compounds, we had talked about the different theories of coordination compounds. We had started with the Werner's theory, which was proposed by the father of coordination chemistry, Alfred Werner. Then we went on to the valence bond theory, and simultaneously at the same time there was another theory proposed by Bethe and Van Vleck called the crystal field theory. We had briefly introduced crystal field theory in our last lecture. Today we are going to do crystal field theory in detail. Now, crystal field theory is based on certain assumptions. The two assumptions are that the interaction between the metal and the ligand of the complex is purely electrostatic or ionic. Crystal field theory assumes that the metal is a point positive charge and the ligand is a point negative charge. If it is in an ionic ligand like chloride, it's treated as a point negative charge, and if it is a neutral ligand like amine or water, it is treated as a point dipole, with the negative end of the dipole approaching the metal ion. Now, when this happens, there are different kinds of electrostatic interactions between the metal and the ligand. The foremost is the attraction, which pulls them together. Along with the attraction, there are also repulsions. There is repulsion between the metal electrons and the lone pair present on the ligands. There is repulsion between the ligands itself if they are negatively charged. And there is also repulsion between the nuclei of the metal and the nuclei of the ligand. This is, however, to a small extent. Now, the whole purpose of doing theories is to basically understand the structure and bonding of coordination compounds. Now, the properties of a particular compound are determined by its valence electrons. Now, coordination compounds are predominantly formed by transition metals. And transition metals are characterized by valence electrons in the d orbitals. So therefore, the whole purpose of the crystal field theory is to understand what does the ionic environment have an effect upon the d orbitals. So in this lecture today, we are going to basically understand the d orbitals, how they are influenced in different ligand fields, octahedral, tetrahedral and square planar. So, d orbitals are 5 in number, although the wave functions corresponding to these d orbitals are 6. But the dz square orbital is obtained by a linear combination of dz square minus x square and dz square minus y square. So, therefore, its electron density is predominantly along the z axis. It also has some electron density along the xy plane and it is called an axial orbital. Similarly, your dx square minus y square orbital has electron densities along the x direction and the y direction. Therefore, this is also an axial orbital. The dyz orbital has electron density between the y-axis and the z-axis. Therefore, it is called a non-axial orbital. Similarly, your dxy and your dxz are also non-axial orbitals. Now, let us assume that we keep this set of d orbitals in a spherically symmetric field or known as an isotropic field. So what happens is, because of the electric field of the ligand, these d orbitals experience repulsion. All the d orbitals experience repulsion to an equal extent. So in an isolated metal ion also, they were degenerate, that is, they had the same energy values. In a spherical symmetric field also, they have a higher energy value, but they still degenerate. Now let us shift our focus from a spherical field or an isotropic field to different anisotropic fields. The first field we are going to talk about is that of an octahedral ligand field. Now this slide shows the orientation of the metal in that octahedral ligand field. Now we can visualize that in an octahedral field, the metal is present at the origin of the coordinate axis, and the 6 ligands are approaching along the 6 directions, that is z minus z, y minus y, x and minus x. We can also see the orientation of the orbitals, both axial and non-axial, with respect to the coordinate axis. And what we see is that the dz square orbital has its lobes along the direction of approach of ligands. The dx square minus y square also has its lobes along the direction of approach of the ligands. The dxy, the dyz and the dxz, their lobes are present between the axes, as we can see in the figure. The xy has lobes between x and y axis. So therefore, their direction is not coinciding with the direction of approach of ligands in an octahedral field. So consequently, what happens is, all the ligands, all the metal orbitals experience repulsion because of the ligand field. But the extent of repulsion experienced by the d orbitals is different. The dz square and the dx square minus y square, which are your axial orbitals, experience greater repulsion in comparison to your non-axial orbitals dxy, dyz and dxz. So therefore, because of the repulsion, there is an increase in the energy of all the d orbitals, but that increase is not equal. So hence the d orbitals which were degenerate both in the spherical field and in the isolated metal ion are no longer degenerate. They split up into 2 sets. The low-lying energy set of non-axial orbitals and the high-lying energy set of axial orbitals. Now, in an octahedral field, we refer to the non-axial orbitals as T2G orbitals, and the axial orbitals are referred to as the EG orbitals. Now, this T2G term and the EG term, they have their origin in a branch of mathematics which is called group theory. Now, the term E represents doubly degenerate. The term T2 represents triply degenerate. And the term, the subscript G, implies that these orbitals are Girard. Briefly reviewing what we have done in atomic structure, a Girard orbital is an orbital which has a center of symmetry when present in a molecule which already has a center of symmetry. Now, an octahedral complex has a center of symmetry or an inversion center. Therefore, we use a subscript G in E as well as T2. And the difference in energies between these two, that is T2G and EG, is known as crystal field splitting energy or delta naught. Now, a better insight into the splitting can be obtained if we view the formation of an octahedral complex as a 2-step process, as shown in the slide. In the first step, the ligands approach the metal ion, forming a isotropic field. So what does this do? This raises the energy of all the 5 orbitals equally. Then in the second step, these ligands form an octahedral field. And this field leads to the splitting of the d orbitals into T2G and EG. So on going from step 1 to step 2, the center of gravity or the barycenter has to be kept constant. So therefore, your Eg orbital would be destabilized by minus 0.6 del naught and T2g orbitals would be stabilized by plus 0.4 del naught. And the difference in energy, as I told you earlier, the sum would be delta naught. Delta naught is also in some books is given as 10 dq. So if it is used, the 10 dq term is used, then the rise of energy of Eg orbitals is plus 6 dq and the stabilization of T2g is minus 4 dq. Now, next what we are trying to do is we will learn how to fill up the electrons in the d orbitals of the metal in an octahedral complex. But before that, I want to introduce a term called pairing energy. Now, what is pairing energy? So, suppose I have two unpaired electrons with parallel spin present in degenerate orbitals. Now, if I have to spin pair them in one orbital, I would need to spend some energy or some energy would be required. That energy is called the pairing energy. Now, the pairing energy is composed of two components. One is the Coulombic repulsion energy, because when I pair the two electrons which are charged species, there would be some repulsion between them which we have to overcome. So, that is the contribution of the Coulombic repulsion energy. The Coulombic repulsion energy decreases as we move down a group. Because the size of the d orbital would increase, you go from 3d to 4d to 5d, the size increases. As the size of the orbital increases, the capacity of the orbital to accommodate the two paired electron becomes better. So, the Coulombic contribution to pairing energy decreases. The second component is the exchange energy. Now, exchange energy is the energy released between the exchange of electrons which have parallel spins. So, whenever I pair two electrons up in an orbital, there would be a loss of exchange energy corresponding to that pair. So, sum of the Coulombic repulsion energy and the exchange energy is the total pairing energy for a particular set of electrons. Now, the pairing energy depends entirely on the metal. So, it is a characteristic property of the metal and has got nothing to do with the ligands attached to the metal in the complex. However, oxidation state plays a role in determining what would be the pairing energy of a particular metal. So, if we look at this table gives you the total pairing energy of different transition metal ions of the 3D series. Now, the third column is the Coulombic contribution to the pairing energy. The fourth column is the exchange energy contribution to the pairing energy, and the third is the total pairing energy. The energy values are given in kilojoules per mole, and the values in bracket are the corresponding values converted in centimeter inverse. So, if we look at the D4 system of chromium 2 plus, we see that the total pairing energy 244.3 kilojoule per mole is a sum of the Coulombic repulsion energy, which is 71.2, and the exchange energy, which is 173.1. For chromium plus, we can see that the exchange energy is less than that of chromium 2 plus. Similarly, if we look at the ferric ion, the ferrous ion and the iron in +1 oxidation states, we see that the pairing energy increases as the oxidation state of the central metal increases. And on an average, the pairing energies are in the range of 40 to 200 kilojoules per mole. So, now we learn how to fill up the d electrons in the metal when present in an octahedral complex. Now, this slide shows you the different configurations. Now, if we have a d0 system, that means there is no electron in the d orbital. So, the electronic configuration would simply be T2G0, Eg0. Now, when we have a d1 system, now d1 system, as we know from a knowledge of atomic structure, that the electron always enters the lowest energy level. So, among the T2G and EG, the lower energy level is T2G. So, the d electron can enter any one of the degenerate T2G orbitals, be dxy, dyz or dxz. In the slide, I have shown the electron in dxy. Now, we come to the D2 system. So, we have to add another electron to the earlier D1 system. So, what are the different options available for this electron? Now, this electron can either pair up with the electron that was present in the D1 system, or it can go to the dyz or the dxz, which were also of the same energy, with a parallel spin or an anti-parallel spin. Now, if we pair up the electrons in the dxy, what would happen? We would have to pay an energy penalty corresponding to pairing energy, because we are putting the two electrons together. As we just did, we have to compensate for the loss of exchange energy and the Coulombic repulsion energy. So, that option is discarded. Now, the remaining two options are either occupying the dxz or the dyz with a parallel spin or an anti-parallel spin. If the electron occupies with an anti-parallel spin, then it would lead to a loss of exchange energy. So, the only option that is left or energetically favorable for a D2 system is when we have the electron present in dyz, as is shown in the slide. Now, the next case is that of the D3 system. Now, in a D3 system, the electron enters the dzx. Now, when we move from a D3 system to a D4 system, what can happen? Now, your T2G is completely filled up. So, is filled up with one spin in each one of the orbitals. So, we have two options. One is we can pair the fourth electron in either one of those orbitals in T2G, or we can push up the electron by giving it an energy delta naught to EG. So, in the first case, the system would be destabilized by pairing energy, and in the second case, we would have to give an energy equivalent to delta naught to push up the electron to EG. So, the option that is adopted by a system actually depends upon the relative energies of delta naught and your P, which is the pairing energy. So, the two cases are as shown in the slide. The first case is when del naught is less than P. When del naught is less than P, it is energetically favorable to pair up the electron in T2G. Now, this implies that the del value is high, so therefore, it is known as a strong field complex. And since the number of electron pairs increases or the number of unpaired spins decreases, this is also known as a low spin complex. The second option is when del naught is less than P. So, when del naught is less than P, it is energetically favorable to promote the electron to EG. So, since the ligand field is smaller in energy, this is known as a weak field complex, and since we have number of unpaired electrons, the total spin of the system increases. This is also known as a high spin complex. Now, this slide shows you the spin states of two complexes of the same metal ion in the same oxidation state and the same coordination number. The only thing that is different is the ligand. Because of the ligand, the value of del naught changes. When the ligand is water, the value of del naught is 10,400 centimeter inverse. When the ligand is cyanide, the value of del naught is 32,850. So, in the first case, in the aqua complex, since the value is less than the pairing energy, the complex becomes a high spin complex. Whereas, in the case of the cyano complex, where the value of del naught is higher than the pairing energy, it is a low spin complex. Similarly, also for the cobalt complexes, if we have a look, the cobalt fluoro complex is a high spin complex as the pairing energy is greater than del naught, and the amine complex is a low spin complex as the pairing energy is less than the field strength. So, now we come to the D5 case. In the D5 case, the configuration is T2G5. Now, the upper part of the slide shows you the low spin configuration, whereas the lower part gives the high spin configuration. So, in high spin, the electronic configuration of a D5 metal ion would be T2G3 Eg2. In a D6 case, in a low spin case, the electronic configuration is T2G6, whereas in a high spin case, it is T2G4 Eg2. In a D7 case, in a low spin case, the configuration is T2G6 Eg1, whereas in a high spin case, it is T2G5 Eg2. Now, for D8, D9 and D10, there is only one electronic arrangement that is possible. So, D8 would be T2G6 Eg2, D9 would be T2G6 Eg3 and D10 would be T2G6 Eg4. So, the entry or the splitting of the electron into the d orbitals basically lowers the energy of the system. Now, this decrease in energy of the system because of the splitting is given a term called crystal field stabilization energy. Crystal field stabilization energy is defined as the energy of the electronic configuration in the crystal or the ligand field compared to the energy of the electronic configuration in the spherical or the isotropic field. So, CFSC is equal to delta E, which is equal to E ligand field minus E isotropic field. So, if the ligand field is octahedral, every electron that enters into the Eg orbital destabilizes the system by plus 0.6 delta naught, and every electron that enters the T2G orbital stabilizes the system by minus 0.4 delta naught. So, therefore, CFSC is expressed as a multiple of delta naught and the pairing energy is also added to it. So, the CFSC or the energy of an octahedral field is equal to, as shown in the formula, minus 0.4 delta naught N-T2G plus 0.6 delta naught Neg plus Mp, where M is the number of electron pairs and P is the pairing energy. So, now let us try to calculate CFSC for some D6 cases. The first case is that of a D6 high spin octahedral complex. The diagram on the left hand side is the spherical field and the splitting is shown for an octahedral field. So, we can see that in an octahedral field, the electronic configuration is T2G4 Eg2. Now, energy for an isotropic field would be the number of electrons, which is 6, into the energy, which is 0 since it is at the barycenter, and since there is one electron pair involved, we add 1p to it. So, E isotropic field is 1p. Now, energy of an octahedral field would correspond to 4 electrons in the T2G, 2 electrons in the Eg, and since there is one electron pair, we would add 1p, giving us a total energy in an octahedral field as minus 0.4 del naught plus p. Now, the CFSC, which would be a difference between the two, would come out to be minus 0.4 delta naught. Similarly, for a D6 low spin octahedral complex, we see that the electronic configuration is T2G6. Now, here in the spherical field there is one electron pair, whereas in an octahedral field there are 3 electron pairs. So, energy of an isotropic field would be 1p corresponding to that one electron pair, and energy of an octahedral field would be minus 0.4 into 6 del naught plus 0.6 into 0 del naught plus 3p, which comes down to be minus 2.4 delta naught plus 3p. So, CFSC comes out to be the difference between these two fields is equal to minus 2.4 delta naught plus 2p. Now, this is another example for a D7 high spin octahedral complex. Here the configuration in an octahedral field is T2G5 Eg2. So, energy of isotropic is 2p as there are 2 electron pairs in the spherical field, which is shown on the left hand side, and energy of the octahedral field comes to be minus 0.8 delta naught plus 2p. So, CFSC comes out to be minus 0.8 delta naught. For a D7 low spin octahedral complex, there is 2 electron pairs in the spherical field or the isotropic field, and there are 3 electron pairs in the octahedral field. So, E isotropic would be 2p, E octahedral would be minus 1.8 delta naught plus 3p, and the CFSC, which is a difference between E isotropic and E octahedral, is minus 1.8 delta naught plus p. So, this slide shows you the CFSC for all the configurations from D0 to D10, both in the high spin case as well as in the low spin case. So, what we see is that the difference when we analyze both the CFSCs, that the CFSC in the low spin case is generally equal to or it is more than that of the high spin case. Now, why do we need to calculate the CFSCs? Now, the CFSCs are important because they give us an idea about the metal ligand bond energies. Now, if you look at this table, if we account for the correction of crystal field stabilization energy, the experimental and the calculated metal ligand bond energy matches. Also, where there are different chemical consequences of CFSC, which we will do later. Now, in the next session, what we will do is, we will understand the crystal field splitting in a tetrahedral and square planar complex. Thank you. Welcome back. In the last session, we were talking about crystal field splitting of d orbitals in an octahedral complex. We had understood how to fill up the electrons in the d orbitals of a metal when the coordination of the metal is 6, that is, the geometry is octahedral. And we also learned how to calculate the crystal field stabilization energy. Now, in this session, we are going to understand how the crystal field affects the d orbitals in a tetrahedral field and a square planar field. Now, a tetrahedron and a cube are geometrically related. We can visualize a tetrahedron inside a cube where the metal is present at the center of the cube and the ligands are present on alternate corners of the cube. So, this slide shows a cube, and in the cube are placed the orbitals, one a non-axial orbital, the dyz, and the other the axial orbital dz square. Now, this cube, let us imagine that the length of this cube is a, and the coordinate axis of the tetrahedron is the twofold symmetry axis of the cube that bisects the edges of the tetrahedron. So, if we look at the figure, the edges of a tetrahedron are actually bisecting the faces of the cube. So, this axis would be along that bisecting point, it will bisect that diagonal. So, you have the z axis, the y axis and the x axis. Now, the dyz orbital in a tetrahedral, the electron in this orbital can only approach within a distance of a/2 to ligand electrons. Whereas, if you look at the dz square orbital, in the dz square orbital, the distance between the dz square and the ligand is √2a/2. So, this distance is 1.414 times more than the distance in the dyz. So, consequently, an electron in the dz square orbital can approach only within a distance of √2a/2 to any one of the ligands. Since the distance is more, the repulsion experienced by the dz square orbital would be more in comparison to the repulsion experienced by the electron in the dyz orbital. So, here in a tetrahedral field also, the degeneracy of the orbitals is lost. It is also split up into two sets, the axial orbitals and the non-axial. But the energy pattern is completely inverse of what was observed in an octahedron. In a tetrahedral case, your non-axial orbitals are destabilized, whereas the axial orbitals are stabilized. And the terminology that is used, like in the octahedral case, would be for a triply degenerate we will use T2 and for a doubly degenerate we will use E. Here we will not use the subscript G because the tetrahedron does not have a inversion center. So, we can also get a better insight into the splitting if we visualize the formation of a tetrahedral complex as a two-step process. In the first step, the ligands approach the central metal forming a spherical or an isotropic field. Now, in this case, all the d orbitals would experience repulsion and the energy would be increased. In the second step, the ligands form a tetrahedral field, splitting the d orbitals into two sets, the low energy E and the higher energy T2. The difference in energy between these two sets is known as delta T. Delta T is known as the crystal field splitting energy. Hence, the T2 orbital would be destabilized by plus 0.4 delta T and the E orbital would be stabilized by minus 0.6 delta T, so that the center of gravity or the barycenter is maintained. Now, this slide shows a octahedral complex and a tetrahedral complex formed from the same metal and the same ligand. The only difference between the two is one has 6 ligands involved, the other has 4 ligands involved. So, if we compare the crystal field splitting energy for the two, that is, if we compare delta O with delta T, what we see is that delta O is larger than delta T. This is also can be seen from the examples that are given. If we have an octahedral complex of cobalt with amine in the +2 oxidation state of cobalt, the value of del naught is 10,200 centimeter inverse. If we have a tetramine complex of cobalt, again in the 2+ oxidation state, the value of delta T is 5,900 centimeter inverse. Similarly, for vanadium complex with chloride ligand, the value of del naught is nearly twice that of delta T. Now, why is this so? One very obvious reason is that in an octahedral complex, we have 6 ligands, whereas in a tetrahedral complex, we have 4 ligands. Greater is the number of ligands, greater would be the repulsion between the ligand orbitals and the metal orbitals, greater would be the crystal field splitting energy. Now, since there are 6 orbitals in an octahedral and 4 orbitals in a tetrahedral, the ligand field decreases by a value of 2/3. Also, if we remember the diagram for the octahedral splitting, we would recall that in an octahedral complex, the axial orbitals coincided with the direction of approach of the ligand. So, a direct interaction always leads to a greater repulsion and hence greater crystal field splitting. Whereas, in a tetrahedral complex, none of the orbitals were in the direction of approach of the ligands. So, this further decreases the crystal field by a value of 2/3. So, delta T roughly becomes equal to 4/9 times the value of del naught. This only applies when we have the same metal and the same ligands. Now, since delta T is so small, the value of delta T always is less than the pairing energy. And as a consequence, all tetrahedral complexes are high spin. Of course, there are 2 or 3 exceptions. One rare example of a low spin tetrahedral complex is that of a D4 chromium 2 complex with 3 bulky ligands and NO plus ion. So, now we come to how to fill up the d orbitals of a metal in a tetrahedral environment. Now, since all the complexes are high spin, first all the orbitals would be singly filled up, and once they have been singly filled up, the pairing of electrons would occur. So, for a D0 case, the configuration would be E0T20 since there are no electron in the d orbital. For the D1 case, the electron enters the orbital of the lowest energy. Now, since dx square minus y square and dz square are degenerate, it can enter any one of those orbitals, giving you a configuration of E1T20. Now, the D2 orbital has an option of either pairing up with the electron in dx square minus y square or occupying dz square either in a parallel spin or an anti-parallel spin. Now, in the first case, where we spin pair the electron, there would be an energy penalty. So, that option is not taken into consideration. In the option where dz square has that unpaired electron in an anti-parallel spin, there would be a loss of exchange energy. So, therefore, the configuration which is energetically favorable for D2 is where the electron is present in dz square with a parallel spin, giving you a configuration of E2T20. Now, since all complexes are high spin, the next electron would go to the higher energy T2 orbital, giving you a configuration of E2T21. Now, in the D4 case, the configuration is E2T22. In the D5 case, the configuration is E2T23. In the D6 case, the configuration is E3T23. Because you can in D6 you can also pair up the electron. You would say that why don't we pair up the electron in D5 itself? But if we pair up the electron in D5 along with the energy penalty of pairing energy, we would also have to spend del naught del T to push up the electron to the higher T2 level. So, pairing starts from the lower energy level of E, giving you E3T23. In D7, the configuration becomes E4T23. In D8, the configuration is E4T24. In D9, it is E4T25, and in D10, it is E4T26. Now, once we know how to fill up the electrons, the next obvious is calculation of the crystal field stabilization energy. Now, crystal field stabilization energy is also known by another acronym called LFSE, which implies ligand field stabilization energy. Now, in this lecture, I have used CFSE, but LFSE is used in many books also, and it is also a correct term and can be used. So, CFSE for a tetrahedral complex would be the difference in energy between the tetrahedral field and the isotropic field. Now, in a tetrahedral field, an electron that enters the E level stabilizes the system by minus 0.6 delta T, and an electron that enters the T2 level destabilizes the system by plus 0.4 delta T. So, the total energy for a tetrahedral field is equal to minus 0.6 delta T NE plus 0.4 delta T NT2 plus MP, where P is the pairing energy and M is the number of electron pairs. So, an example for calculation of CFSC for a tetrahedral complex. Now, this example is that again for a D6 metal ion. Now, the spherical field which is shown on the left has one unpaired electron, and the tetrahedral field has a configuration E3 T23 with one unpaired electron in the E orbital. So, the energy of the isotropic field would be 1p. The energy of the tetrahedral field would be minus 0.6 into 3 plus 0.4 into 3 delta T plus 1p, giving the value of minus 0.6 delta T plus p. So, therefore, the CFSC, which is the difference between these two, would be equal to minus 0.6 delta T. Now, this table gives you the CFSC for tetrahedral complexes or for all the DN systems from D0 to the D10. Now, suppose we have been given a metal and a ligand, and the complex is MLN to some charge, say M minus. Now, will del depend upon these four entities forming the complex? That means four entities which are a part of the complex, or in other words, would M, which is the metal, would L, which is the ligand, N, which is the coordination number, and M minus, which is the charge on the complex, make a difference on the value of del? The answer is yes. All these factors influence the value of del. The first factor we are going to study is the oxidation state of the metal ion. Now, if we look at the example given, here we have a complex of metal with water, where the coordination number of the metal is 6. The charge on the metal in one case is 2 plus and in the second case is 3 plus. So, what we see is that the value of del naught is nearly twice when the metal is in the 3 plus oxidation state in comparison to when the metal is in the 2 plus oxidation state. The reason is the greater is the charge on the metal, the greater would be the approach of the ligand towards the metal, greater would be the electrostatic interaction, which would lead to a greater repulsion and hence higher value of del. So, when your metal is the same, ligands are the same, coordination number is the same, the charge makes a difference in the value of del. The next example, if you look at the next example, here we see cobalt, rhodium and iridium. So, in this slide we can see the values of del, that for the hexamine complex of cobalt, the value is 22,900. For the hexamine complex of rhodium, which is just below cobalt, is in the cobalt group only, the value is 34,100, whereas for iridium it is 41,000 centimeter inverse. So, what is the difference between the three metals? The difference between the three metals is that the cobalt belongs to the first transition series or the 3D series, where the valence electron enters the 3D orbital. Rhodium belongs to the 4D series, where the valence electron enters the 4D orbital, and iridium belongs to the 5D series, where the valence electron enters the 5D orbital. So, as the size of the orbital increases, its interaction with the ligand increases. More is the interaction, more would be the crystal field splitting. So, because of this, the complexes of the second and the third transition series are generally low spin complexes. The third factor, which is the number and the geometry of the ligand, we have already explored earlier, and we know that delta T is roughly equal to 4 by 9 delta naught when the metal and the ligands are same. The next factor is the nature of the ligands. If you look at the given table gives you delta naught values for some octahedral complexes of 3D metal ions. The ligands are given in the second, third, fourth, fifth and sixth column. So, if we look at the chromium 3 plus, we see that as we move from chloride to water to amine to ethylene diamine to cyanide, the value of del naught increases, and the same is with all the metal ions given in the table. So, what was done was that del naught values were calculated, or experimentally not calculated, they were experimentally determined with a large number of ligands for a large number of metal ions. So, in all the cases a pattern was noted, and that pattern was recorded as the spectrochemical series. So, what is spectrochemical series? It is an experimentally determined series of ligands, in which ligands are arranged in increasing ligand field strength. So, if we look at the series, the lower end of the ligand series are the weak field ligands, and the higher end of the series have strong field ligands. Now, the problem with the spectrochemical series is that it, if you look at the assumptions of the crystal field theory, one of the assumptions is that it is because of a ionic interaction between the metal and the ligand. So, if the ligand is charged, the electrostatic interaction or repulsion should be more. But if you look at the series, the anionic ligands are the weak field ligand, most of the anionic ligands. The hydroxide ligand is a weaker ligand in comparison to water. And if you look at the neutral ligand, water and amine, the dipole moment of water is more than that of amine, but still water is a weaker ligand in comparison to amine. Similarly, carbon monoxide is a neutral ligand, but still it is a very strong field ligand. So, these are some limitations of the spectrochemical series, which we will study in detail later. So, generally a field is considered as a strong field if the del value is greater than 30,000 centimeter inverse. This is a generalization, and it is a weak field ligand if del is in the range of 7,000 to 30,000 centimeter inverse. So, suppose I ask you that I give you a metal and I give you a ligand and I say, can you just by looking at the metal and the ligand make an educated guess whether it is going to be an octahedral complex or a tetrahedral complex? The answer is yes, if the formula of the complex is given to you, because if the formula is ML6, you automatically would realize that the coordination number is 6. So, for a coordination number 6, the more common geometry is octahedral. In some cases also trigonal prismatic is noted, but those are rare cases. Similarly, if the coordination number is 4, then the geometry would be tetrahedral or square planar. Now, square planar is formed by D8 metal ions in a strong field. So, obviously, we would say that it would be tetrahedral. But what if the chemical formula, the molecular formula is not given to you? How will you decide whether it is an octahedral complex or a tetrahedral complex? We will see how. So, if you look at the slide, this slide gives you the value of CFSEs for the octahedral as well as the tetrahedral case for different metal ions. Now, if you look at the values, you would say that the CFSE for an octahedral case is always more than the CFSE for a tetrahedral case. Now, in this table, the CFSE for tetrahedral has been calculated by assuming that delta T is 4 by 9 delta naught. So, a better idea of these numbers can be obtained if we look at the graph of these numbers. So, this graph is a plot between your minus LFSE, or I told you can also use the term LFSE, which is in units of delta O, which is along the y axis, and the number of d electrons, which is along the x axis. And the blue dots are the CFSEs for Dn metal ions in the tetrahedral geometry, and the pink dots are the CFSEs for DN metal ions in an octahedral geometry. So, what we note here is that the CFSE for a tetrahedral is always higher than that of an octahedral. The reason is because it is energetically more favorable to form 6 bonds rather than 4, and as we see that CFSE is also higher. And if we look at the D3 case and the D8 case, we see that the CFSE difference between an octahedral and a tetrahedral is maximum for D3 and D8, followed by D4, D9, then comes D2, D7, and finally D1, D6. So, it basically means that an octahedral geometry, favorability of an octahedral geometry also depends upon coordination, upon the electronic configuration. So, the favorability variation with electronic configuration, as I told you earlier, is D3, D8, then we have D4, D9, D2, D7, then comes D1, D6, and for D0, D5 and D10 cases, the CFSE is 0 in both the cases, be it octahedral or be it tetrahedral. So, therefore, it does not matter for those particular configurations. Also, if you look at the units of the graph, they are in del naught. So, any factor which increases the value of del naught would increase the chances of an octahedral coordination in comparison to a tetrahedral coordination. So, these factors which we have studied earlier are, if you have a metal in a higher oxidation state, the difference in CFSE would increase and it would favor the octahedral coordination. If the ligand is a strong field ligand according to the spectrochemical series, the favorability of octahedral increases. If your metal is from the 4D or the 5D transition series, again the difference in the CFSEs would be higher and it would favor the octahedral coordination. Then the question is, when will we ever get a tetrahedral complex? Yes. We can expect tetrahedral geometries if the following conditions are satisfied. If we have a large ligand, because when the ligands are large or bulky, then there occurs a crowding in the geometry if it is octahedral, and the preference is more towards a tetrahedral geometry. If the ligands are highly charged, then there are repulsions between them and the tetrahedral geometry is favored. If the ligand is a weak field ligand, then the loss in CFSE is less and the tetrahedral geometry is favored. And if the metal ion is D0, D5 in the high spin state and D10, then the tetrahedral geometry is preferred. And also D1, D6, D2, D7 metal ions are preferred if the loss in CFSE is less. So, the table below gives you examples of some regular octahedral complexes, and we see that an regular tetrahedral complexes, and we see that the tetrahedral complexes are favored or preferred when we have a D0, D5 high spin, D10 metal ion with large ligands, highly charged ligands or weak field ligands. So, now since we have studied the tetrahedral and the octahedral geometry, let us try to do some examples or questions. Now, suppose you are given this complex of iron, which is the hexacyanoferrate complex of iron in 2+ oxidation state, and we have to determine the structure and the number of unpaired electrons for this complex. Now, since the formula is given to you and we can see that cyanide is an anionic ligand with and along also with it, it is a monodentate ligand. So, the coordination number of iron would be 6. So, if the coordination number is 6, then the geometry would be an octahedral geometry. Now, iron here is in the 2 plus oxidation state. So, therefore, the electronic configuration of iron would be in the 3d6, because iron is argon 3d6 4s2, iron 2 plus would be 3d6. So, in an octahedral complex, since cyanide is a strong field ligand, the configuration is T2G6 Eg2 and T2G6 Eg0, and therefore, there are no unpaired electron and the complex is diamagnetic. Similarly, we can also work out for hexafluorido-cobalt complex, and the structure is octahedral since fluoride is a monodentate ligand, and the electronic configuration of cobalt 2 is T2G4 Eg2, as your fluoride is a weak field ligand according to the spectrochemical series, giving the number of unpaired electrons as 4. So, now we have learned how to do the crystal field splitting in an octahedral and a tetrahedral case. Now, in the next session, we will talk about the crystal field splitting in a square planar geometry and also learn about the importance of CFSC by doing some applications of crystal field theory. Thank you so much.
With this note, thank you, ma'am. Thank you so very much for giving us a very, very precious session. And dear friends, we believe that you have learnt a lot today. And if you want to learn more, or if you want to have a more on what we have studied today, then you can definitely watch our YouTube lecture. The lecture is going to be uploaded on YouTube very soon, and with the help of the lecture, definitely you can revive what you have learned today. And afterwards, if you feel that you have any question, then do write to us at info.cc@nic.in. We would love to solve your queries the next time when Dr. Shilpa Mehta visits our studio. Till then, take care. Goodbye. Thank you, ma'am. Thank you once again.
Thank you so much.